Okay, so here's class 11, where we're continuing on with, I believe this is chapter 5, maybe? Yeah. And we're talking about Bernoulli's and the energy equations. And here we're going to add some stuff to Bernoulli with respect to pump and turbine power, talking about head losses, and talking about efficiency. So here is our cartoon for today. We show wetted using this control volume, and where we have mass flowing in, and we're putting work and I should say power into the system, and we're removing heat from the system. So what we're really going to do is we're going to use Reynolds transport theorem applied to energy, and note that it becomes Bernoulli. So just as, taking a step back and talk about work and energy as it pertains to Reynolds transport theory, we first want to talk about what happens to the system. Now remember, the system is like this chunk of mass, the original mass. And so symbolically, that energy that's in the system is comprised of the net heat rate coming in and the net work rate or power coming into the system. And that net is the in minus the out. So here is where we move on to the Reynolds transport theorem. And we treat that capital B from Reynolds transport theorem as if it's capital E. And we'll treat this lowercase b, of course, it's going to be capital E per mass. And we'll call that little e. So as we're going to write out Reynolds transport theorem, we take the partial derivative with respect to time of the energy that's within the control volume right here. And that's a particular term we'll see in a second. So I put a little brace underneath it a little early. Whoops. Going through the control surfaces, so that's the control volume. Whoops, I meant to put a control volume there. Going through the control surfaces, we have the velocity dotted with the normal unit vector times dA. And we have to recall that this portion right here is really the mass flow, right? And so this is all of the things passing through control surfaces. And this ensures right here that it's going to have the correct sign convention in terms of things entering, because the velocity, this is an outward normal facing unit vector. That's perpendicular to the control surfaces. So this right here is going to give us the correct sign conventions for coming in and out, and making sure that it's only velocity that's perpendicular to the control surfaces. We'll see that that's going to be an important thing when it comes to linear momentum soon. So really it's the mass flow that is the transport in Reynolds transport theorem. Because it's the mass flow that's the thing that's transporting the thing we're moving. In this case, it's the energy per mass. And that's going to equal, right? So that's actually, I'm going to move that stuff over onto this side. That's going to be what happens to that original mass, right? So the net in plus the power net in of the system. This term over here is an accumulation term. You could think of it as storage, right? So we might somehow magically store energy within our control volume. But most of the time what we care about in terms of Reynolds transport theorem for us is going to be this guy right here. Got to be careful here that this Q that we're talking about is not the volumetric flow rate. So I would just warn that to some students that might be taking thermodynamics at the same time, and sometimes the sign conventions are different in thermodynamics than in fluid mechanics. So just be aware of that. So I have a little brief aside here to talk about power, right? And define power. And we know that it's going to be work per time. Recall, though, that work is force through a distance. So force times velocity is power. So we could, if we wanted to use a dot product thing going on here, we could say it's the force vector dotted against the velocity vector. And that dot product makes for a scalar, which is important for us because we know that power doesn't have a direction to it. But just as a thought experiment or something, I'm going to get rid of the vector hats because we already established that it's going to be dot is going to turn to a scalar. What if we were to divide this by area and then multiply the velocity, which I'm going to use capital V now for velocity, times area, right? So we've divided by area and we've multiplied by area. And notably, conceptually, that this is going to be our pressure, or let's say a change in pressure times volume and flow rate, right? Because we know that velocity times area is a volumetric flow rate. And maybe that change in pressure, we might want to turn this into, because a head, in terms of the idea of head. Because we remember in the last class, we said, well, we could do a Bernoulli that's instead of terms of pressure, we could do it in terms of head. So we could have the height of our head times our gamma, and that's going to equal a change in pressure, right? And this h is not necessarily a height, but it may be a representative height. That's what we have for the idea of head, is a representative height that, when combined with gamma, represents the pressure. And then we have a volume flow rate. So if we want to get power in terms of head, all we have to do is multiply by gamma and the volumetric flow rate. I also put it into here just as a kind of an aside that a conversion for horsepower, which also often comes up, is 550 foot-pounds or pound-feet per second. I also mentioned that if a good thing to also know about when it comes to power is that power is equal to torque times RPM. So just those ideas are good things to kind of keep in the back of our minds. That was sort of an aside. Moving back over to the pertinent thing where we're taking Reynolds transport theorem and applying it to energy. We have internal energy. In this case, we'll think of this as thermal energy using capital U, and we could find what the state of the energy is. Like a lot of times for thermo, we're dealing with heat flows, but this is just the current state of thermal energy. Could be found by mass times the constant volume, specific heat times temperature, right? So that's the state of a thermodynamics or the thermal energy at a given time. Here's a strain energy, which is kind of related to work. That's the same kind of work that we were talking about up before, force through a distance, that kind of work, solid mechanics kind of thought of work. Well, that could also be said that that's going to be pressure times area times a distance, right? So that'd be force, pressure times area, okay. Or we could have that area times a distance could be a volume, right? So pressure times volume. And I often will think about the banana curves that you maybe will be familiar with. I think this is a diesel cycle I just drew right there. But we have a PV diagram right here. And we know that the area inside the banana curve is going to be work, right? So that's sort of a strain energy type of energy that we want to consider. We also have kinetic energy, remember from dynamics, 1/2 mv squared. We have potential energy, also from dynamics. This is the gravitational potential energy. We left out spring potential energy, but that's actually kind of related a little bit to strain energy, if you could imagine that. We're not talking about electrical, chemical potential, magnetic, atomic, solar, whatever. So these are really the energies that are possible for our context here. And full disclosure, we're usually going to ignore the temperature changes energies. They turn out to be small in many of the scenarios we have. So, because we're talking about Reynolds transport theorem, this is the big E. We want to talk about the little e, and so we can just divide all of these above by mass. And if you do, these all simplify down. Notably, this turns into pressure times specific volume, which is the same thing as pressure divided by rho, and 1/2 v squared here for the kinetic energy per mass. And now we just have G times Z, and so here comes E, and we could pull this back into what we had going through the control volume, right? And I already mentioned this was the storage term. So if you don't have any storage term, that goes away. And what we're left with is this portion connected to this portion right here. So what we essentially have is the integral across all the control surfaces of the U. So I'm going to leave out and I'm just going to keep that in there. P over rho v squared over 2 plus g z, and that's rho v dotted normal right there. Oh, this would be a caret hat because it's a unit vector. dA, and equal to the Q net in, rate of heat, and the W net, so the rate of work net in. So if instead we go along a streamline and we say we have a conservation, we don't have anything coming in externally to the thing. Well, we could say along a streamline, ignoring these guys, right? Ignoring the internal energy changing, we end up having P over rho plus V2 squared over 2 plus GZ, right? And so we could say that this is out times M dot out minus P over rho plus V squared over 2 plus GZ in times M dot in. And set that equal to 0 if this hasn't changed. Well, that right there, that's Bernoulli. And we got to the same place. We were kind of fast and loose with a couple things, but we do know that we can have Bernoulli is going to be an energy balance. We saw all of these different kinds of energies, specifically these 3 types of energies are being balanced on the in and the out. I think I'm going to keep on going. Now I'm going to make another video. Okay, so we'll go into the next video here this is class 11, so that's video 1, and we'll pick up where we left off.